Welcome to AI Frontiers, your spoken word guide to the most current developments in machine perception. Today's episode is titled Vision Unleashed, AI's New Eyes, featuring insights from 16 leading computer vision papers published in May 2025. Our focus, exploring the latest breakthroughs in computer vision research, synthesizing findings across multiple domains, and tracing the trajectory from perception to reasoning and physical realism. This episode highlights trends shaping tomorrow's intelligent systems, providing context and clarity for researchers, enthusiasts, and anyone interested in the future of artificial intelligence. Let's begin our journey through the rapidly evolving landscape of computer vision. In this episode, your guide to computer vision frontiers is structured to set the stage for why computer vision is fundamentally transforming technology today. This discussion identifies the dominant research themes emerging from recent literature, explores technical innovations and methodologies, and spotlights pivotal findings and anticipated future trends. The objective is to equip listeners with the knowledge and perspective needed to follow and understand the rapid pace of advancement in computer vision, situating each research contribution within the broader evolution of AI-driven solutions. What is computer vision? At its core, computer vision enables machines to interpret and understand images and videos, giving rise to automated systems that can perceive the world visually. This capability powers critical applications ranging from healthcare, such as advanced medical imaging and diagnostics, to robotics, urban planning, and beyond. Unlike earlier approaches limited to simple pattern recognition, today's computer vision seeks to replicate, and sometimes exceed, human-level visual perception. The field now integrates not only visual understanding, but also language, audio, and physical reasoning, making it fundamental to modern artificial intelligence and its deployment across diverse industries. The first major theme emerging from the latest research is the fusion of vision with language and audio. Vision-language models are at the forefront of this trend, enabling systems to process and relate information across multiple modalities. For instance, the SAT-2 SOUND framework, authored by Connell and colleagues, predicts environmental soundscapes directly from satellite images by synthesizing data from vision and audio. GeoVLM and GeoRanker further enhance geolocalization tasks by leveraging vision-language matching, improving both accuracy and interpretability. This multimodal fusion unlocks new applications, ranging from immersive environmental simulation to advanced monitoring in urban and ecological contexts. A second dominant theme is intelligent representation learning. Many recent papers demonstrate how contrastive and cross-modal learning approaches align images, text, and audio within shared feature spaces. This enables models to develop robust, transferable features that generalize effectively to new scenarios, supporting zero-shot generalization, where models adapt to novel tasks without retraining. SAT-2 SOUND and GeoVLM exemplify the power of shared multimodal representations. The technical concept of contrastive learning is central here. Models are trained by comparing positive pairs, which are semantically related, and negative pairs, which are not, thereby learning to distinguish meaningful similarities and differences across modalities. Theme 3 centers on efficiency, scalability, and autonomy in model architectures. As computer vision models scale up, efficiency becomes critical for practical deployment. Innovations such as sparse attention mechanisms and trainable architectures reduce computational costs significantly. For example, the faster video diffusion framework, developed by Zhou and collaborators, enables efficient video synthesis with reduced hardware demands. Simultaneously, self-supervised and unsupervised learning methods are reducing reliance on labeled data, making large-scale learning more feasible. The IPANS framework, introduced by Song et al., allows for rapid plant phenotyping without manual annotation, accelerating research applications in agriculture and biology. The fourth theme highlights the growing emphasis on reasoning, interpretability, and physical realism within computer vision. Modern models are increasingly designed not only to perceive but also to reason and provide explanations for their outputs. VT-Bench by Zhou and colleagues benchmarks the complexity of visual question answering, advancing the interpretability of AI systems. Meanwhile, works such as Fine Fizz by Wang et al. and Kin Twin integrate biomechanical and physics-aware modeling, embedding physical laws into artificial intelligence to generate realistic motion. This technical approach, known as biomechanical modeling, enhances trust, safety, and interpretability, attributes essential in domains where reliability and transparency are paramount. Cross-paper analysis reveals several key findings that are shaping the future of computer vision. Multimodal soundscape mapping, as pioneered by Canal and team, achieves state-of-the-art results in predicting environmental audio from satellite imagery. Distance-aware ranking, addressed by Sun and colleagues, advances the accuracy of image geolocalization. Goupy et al.'s innovation, frozen backpropagation, substantially reduces the hardware costs in spiking neural networks, a critical step for energy-efficient AI. Unsupervised plant phenotyping, demonstrated by Som et al., is revolutionizing agricultural research by automating complex trait extraction. Finally, recent advances show that perception and reasoning are now tightly coupled, as in the work by Wu et al., enabling general AI agents to act with increased autonomy and robustness. Methodological advances across the field are also noteworthy. Vision language models are being leveraged for joint image-text understanding, enabling cross-domain retrieval and semantic alignment. Contrastive and cross-modal learning approaches are promoting the development of robust generalized features that support zero-shot tasks. Self-supervised and unsupervised learning strategies are scaling model training by extracting structure from unlabeled data, increasing scalability and applicability. The adoption of sparse attention mechanisms and efficient architectures is making large-scale deployment more practical. Finally, the integration of physical modeling serves to bridge simulation and real-world tasks, enhancing the realism and safety of AI-driven systems. A seminal paper featured in this episode is SAT2SOUND, authored by Connell and colleagues. SAT2SOUND maps environmental soundscapes for any location on Earth using satellite images, employing a unified vision language framework that enables multimodal concept learning. The system is capable of zero-shot audio and caption generation, creating immersive experiences and outperforming prior methodologies. Its innovation in cross-modal, concept-driven learning has opened new pathways for simulation, urban planning, environmental monitoring, and gaming, exemplifying the transformative potential of integrating vision, language, and audio within a single framework. Another influential contribution is the frozen backpropagation technique introduced by Goupy and collaborators. This work addresses persistent hardware bottlenecks in spiking neural networks by relaxing the requirement for weight symmetry through the use of frozen feedback weights. As a result, high accuracy is maintained while achieving dramatic reductions in hardware cost. This development makes energy-efficient artificial intelligence feasible for edge devices and always-on systems, marking a significant step forward in practical neuromorphic learning. The method's balance of computational efficiency and learning effectiveness underlines its importance for both algorithmic progress and future hardware design. A third seminal paper is IPANS, authored by Song and colleagues. IPANS is an interactive, unsupervised framework for rapid plant phenotyping, achieved by fusing neural radiance field and SAM2 segmentation technologies. This approach creates detailed three-dimensional point clouds from simple image inputs, eliminating the need for manual annotation while maintaining high accuracy and delivering fast results. The IPANS framework accelerates crop research and intelligent breeding, making large-scale trait-specific analysis feasible for agricultural science. Its autonomy and real-world impact are advancing both biological research and food security initiatives. Looking toward the future, several promising directions emerge for computer vision research. Deeper multimodal integration is expected, with systems combining vision, language, audio, and physics for richer understanding. Increased autonomy will be realized through self-supervised and unsupervised methods, reducing dependence on labeled datasets and expanding applicability. Embedding domain knowledge and physical laws into AI models will enhance realism, safety, and interpretability. Efficient and scalable models will underpin deployment in real-world environments, while a growing emphasis on explainable, human-centric AI research will ensure that these advances remain trustworthy, accessible, and beneficial across disciplines. The synthesis of this episode's content was achieved using advanced AI tools and expert human review. Text generation was supported by GPT 4.1 from OpenAI, while DeepGram facilitated high-quality text-to-speech synthesis. Visual assets were produced with Grok. All content was subsequently reviewed and refined by human experts to ensure technical accuracy and clarity. However, some minor oversights may remain. Listeners are encouraged to consult the original references for complete details. All cited works are included for further exploration, supporting continued learning and discovery. As we conclude, remember that AI Frontiers is committed to keeping you at the leading edge of artificial intelligence research. For more deep dives into topics like computer vision, subscribe to our YouTube channel. Join the discussion, share your feedback, and help expand the conversation around the future of AI. Thank you for exploring the frontiers of computer vision with us. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprint server.